Hello. So this is the exam 4 review slides for summer 2017. With that, so the it's going to be a lot of reactions. It's going to be from chapter 8 and chapter 22. So with that, and so for a lot of these are going to be reactions to know. So with that, so we're going to go over those first. So with that, and so if you want to make, so for example, if you want to make a double bond, right, you can hit this with KOH in the presence of an alkyl halide. You can also use sodium hydroxide too. That'll work, but that'll rip off a hydrogen next door. It's just an E2 reaction. So you're gonna rip this away. This will collapse, kick off your leaving group, and so you can do it on either side, right? So you can make these two products. You can also do the same sort of reaction with an alcohol here, an OH group, but you do it in acid, and it gives the same results. You can also add once you have the alkene. Right, so with that you can add HX across it. So H goes on the lower number side, X goes on the higher number side. Right, so this is secondary, this is tertiary. Okay, and so the X is X, and then by this being X in the halide, so chlorines, bromines, and so on. Now, however, I think I forgot to write this. If you wanted to instead do this reaction, but you wanted to get it on the, if you want to get that. Say the bromide on the higher numbered side, or the lower numbered side, so the complementary, so put it on this one, you're going to have to put HBr in the presence of peroxides. Okay, and so if you want to get get the complementary reaction. Now if you just had plain halides, you're just going to put the halide across here, so if this is Br, it'd be Br. Okay, now however, if you do it with water around, the first halide adds. Okay, but then the second time it's actually the water adds, and so you end up with an OH group on the other side. So with that's called a halohydrin. Now for these, for the mercury acetate or borane, so these are actions you're actually adding water across here, right? So you're adding HOH across here. So with that, but for the mercury one, you put it again. You're going to put it on the tertiary, well, the higher number side, so tertiary, secondary here. For the borane ones, you're going to put it on the lower numbered side, the OH there. Okay. Now with this is just regular hydrogenation. You can also do palladium on carbon. You'll take double or triple bonds, taking them down to the alkane. With the osmium, remember you put the OHs on here, and generally you're going to put them. They're going to go on the same face. It's a syn addition. Now with a straight chain like this, you're going to get free rotation, so it doesn't matter. But if you're going to do this on a chain, on a ring, they're going to go on the same side. Okay. So with the ozone, okay. So with that, so you slice this, and you're going to get the C double bond O. Carbonyls here, so if you have carbon-carbon double bonds, you're going to get 2 CO bonds here, so here and here on each one of those. This hydrogen, right, we don't, we just leave it as an H, because if you were to do it in, it's usually hot permanganate here, this aldehyde, you would still get the same slicing, okay, but the aldehyde wouldn't survive, and so you turn it into a carboxylic acid, okay. With the pyridate, again you get cleavage, but instead of cleaving on the double bond, you cleave between 2 adjacent OH groups. Now the OHs have to be pointed in the same direction, okay? And then what comes out is where the alcohols are. That's where these they become C double bond O's. So you slice it in here. Okay. For these two, you're going to make cyclopropane. So chloroform and base, you can use KOH or sodium hydroxide. Doesn't matter. You're going to make the triangle, okay, so you're going to make it here, but with the chloroform, you're going to put chlorine on there, okay. If you do the Simmons-Smith, which is CH2I2, the zinc-copper amalgam, again, you're going to just put the triangle where that double bond was, okay, but here it's going to be that CH2, so this CH2 ends up being that CH2. For the alkyne reactions, for a lot of these things, it's just multiple versions of the alkene reactions. Okay, so for here, so sodium hydroxide or KOH, doesn't matter. You're just doing the E2 reaction first. Okay, so you're gonna need excess of this. Okay, so this comes in, grabs this, collapse, kick away, and then you're gonna come and grab this one, collapse, kick away. You're just gonna do it twice to make. So between those two halides is where that triple bond is going to be. And so if you had HX across here, right, you're gonna go on the. It's still going to follow the same Markovnikov rules. The H is going to go on the higher number side. This, and then tertiary is going to go lower number, stuff like that. But the halides end up going on the same carbon. So it's not like H and so it's not like bromine. Here it's going to go. Both bromines would go on the same carbon. With HX, again, you're going to need excess for this. Here, you're just doing it twice. For the mercury and the borane, so for these, you're going to go to this intermediate here. You're going to just do the normal reaction, okay? But this is unstable, and so it actually tautomerizes down to here. And so the molecule would rather have the double bond O here on the C double bond O than have the carbon-carbon double bond up next to this, off of this alcohol here. It's just going to be a lot more stable. So as soon as it adds the first time, it snaps shut. So you're still going to be so for this one, you're still going to put this on the mercury is going to be the higher ordered side, and the borane is lower. Now, if it's internal, it doesn't matter. Okay, it's really just at the terminus that you have to worry about it. So for here, this is secondary versus primary, right? So for the mercury, you're going to put that oxygen on that secondary. For the borane, you're going to put it here, and so after it snaps, after it tautomerizes, you're going to get that. Okay, so more alkyne reactions, right? So regular hydrogenation is going to go to the alkane. Okay, if you do the H2 at the Lindlar, you're going to get the cis alkene, right? Because the hydrogens add to the same face. Okay, so they're both pointed in the same direction away from the double bond. Now, lithium and ammonia, this also sometimes written sodium and ammonia. It works the same way. Here, the hydrogens is going to be trans, right? So this is going to be cis. This is going to be trans because this hydrogen is pointed that way away from the double bond. This one's pointed this way. Okay. Now for the ozone and the permanganate, you're still going to get the slicing. Okay, but for here, you had a carbon-carbon triple bond, so that means you're going to have, off of each one of these carbons, you're going to have 3 CO bonds, and so the only way that you can do that is to do the carboxylic acid. So no matter which one you do, you're going to get carboxylic acids on the other side. Now, the quirky thing is, if it's a terminal, you're going to end up with carbonic acid, that's going to get further oxidized up to you're going to have the formic acid, which gets further oxidized to formic acid or carbonate, which decomposes to CO2 plus water. Okay, so if it was a terminal, what you'd only see in solution is basically the 1/2. That extra carbon would just go away, something like that. And so this, like that, and it works the same way with permanganate or the ozone. With this one here, remember, sodium amide will take off a terminal hydrogen, which it's just a base reaction, and so this can come in, react, and do a nice SN2 reaction on a primary bromide to extend out the carbon, to make a new carbon-carbon bond, extend out the chain. Okay. Now there are a couple carbohydrate reactions to know, and they just involve the top and the bottom. Okay, and so for sodium, with just sodium borohydride, it's just acting here at the top, and it goes from a double bond to a single bond, a C double bond O to just a CO bond, and so you end up with the OH. Bromine, so for that bromine oxidation, it just converts this into what is essentially an OH here, right? So that is, right, carboxylic acid here. So it just works at the top. Now, reacting down here at the other end is really hard, so you're going to need an enzyme to do that. But if you do nitric acid, you're going to make both ends into carboxylic acids. Okay, so one way you can see this is to say, like, predict reagents. So you're going to say, how am I going to go from here to here? Okay, and so in this way, so we're going to add bromines on either side. You look down on this list and say, here. So by that, so HBr, if we just HBr, it'd just be H and Br. But since we have Br2, right, you're going to do this. If we had Br2 with water in here, one of these would be replaced with, it would be like Br and OH. So for this one here, right, we're converting the alkene to the alcohol, okay. But notice it's going from tertiary to secondary, so we put it here, and so with that. So how how do you turn an alkene into an alcohol but put it on the lower side? It's the borane here, so A. You're going to need to use A. Okay, so there's going to be the predict the product questions. Okay, so zinc, you're going to actually need acid here. So for the zinc, or excuse me, with the ozone, with the zinc, right? So there are hydrogens here. Okay, so when we slice it, 0, 0 or OO, right? It's going to go H like this. You're just going to slice that right there. Yeah, you end up with aldehydes at the end. Okay, so for this one, we're just adding HBr across here, but remember the Br likes to go on the higher numbered side, so this secondary, that's primary. So we're just going to add it twice, Br. Right. And for this one, remember the osmium, we want it to add OHs, but it's a syn addition, so they're going to be going on the same side. Okay, so for this one here, right, so we're going to be, this converts an alkene into an alcohol, but this one puts it on the higher numbered side, so this one is, right, so it's secondary, this is primary. Okay. So it's going to turn it into that. Don't worry about the MCPBA. So for this one, we're going to be adding chlorine across the alkene, but we have the presence of water, and so here this is tertiary, right? This is primary. So the first one, the chlorine's the first thing to go on, so that's going to be, put a chlorine here, and then the water adds, and so you're going to end up with an OH on this side, on the higher numbered side. If the water wasn't there, you'd have a chlorine there, but since you have water in there, it becomes an alcohol. Makes the halohydrin. Okay. For the multi-step synthesis, so you're going to see one that's similar to the design of synthesis you had on exam 3, but you're also going to get one like this as well. And so the question becomes, so you start here, so you have to start from this product, but so these two carbons here are those two carbons there. Okay, so how do we make a methyl ketone like this? Well, we could use like ozone and or pyridate or something like that to slice, but we'd have to build up the carbon and then cut it. Because if we cut this, we'd be 1 carbon short, right? It'd be 1, 2, 3, 4, 5, but we need 6 carbons. Okay. The other way that we could do it is to do the mercury acetate. So right, and use a triple bond. So it's going to put the OH here initially, and then that tautomerizes to the methyl ketone. So how do we make an alkyne here? Well, you think back to the list, right? If we had this, and say put in a lot of OH, sodium hydroxide excess, boil it up, it's going to do, basically it's going to do 2 E2 reactions. First one puts on a double bond, second one puts in that triple bond. Okay, so how do we convert this into here? This one's just dumping in bromine, and that'll add. This puts bromines on the other side. So there's your synthetic route. Okay, so now onto the carbohydrate section. So for here, you're going to get this chart here. Okay, that tells you the names, and so I'm looking for things like aldo triose or something like that. Okay, so you need to tell me if it's an aldo or keto, and then how many carbons there are. So this one here, there's a ketone, right? Because there's carbons on both sides, right? So it's a keto, but there's 1, 2, 3, 4, 5, 6, 7. So don't forget about this one here. So come down here, ketoheptose. So for this one here, there's an aldehyde, right? Because it ends in an H, so it's an aldo. So 1, 2, 3, 4, 5, 6. Now don't count the hydrogen. We're just counting carbons. So don't count that hydrogen. So with that, so it's an aldo, and then there's 6. So aldo hexose. Okay. Okay. So for this one, so DNL. So if it's in a straight chain like this, all you got to do is you got to look at this one here. If it's pointing to the right, it's a D. If it's pointing to the left, it's L. Right, left L. So here, this one here, so this is D, right, because it's pointing to the right. This one here, it's pointing L, or pointing to the left, so it's L. Here, it's pointing to the right, so it's D. Now for for cyclic versions, what you're really looking for is this carbon group that's hanging outside the ring. If it's below the ring, it's L. Okay, if it's above the ring, it's D. It doesn't matter which way that OH is pointing. It's just, is this carbon group, is it above the ring or is it below? That's it. That's all you gotta look at. Okay. So for the L forms, what we're doing is we're just making the mirror image. Okay, and then the important ones are actually this right here. This and that. Those two carbons there, those are not chiral, right? Because this is a CH2, right? And this one only has 3 things hanging off of it. So it doesn't really matter how you point. So you can either go like this, just do a straight mirror image, and so, right? So left, left, right. So we need to go right, right, left. Or you could just keep those fixed like they were, like this. I don't care. It's this one. It's those in the middle that are the important ones. So right, left, right. So ours needs to be left, right, left. And notice how these two are now pointing left, so they're the L sugars. Okay. So for the Killiani-Smith reaction, so for diarabinose, okay, so it's here. So you need to just find this. So OH, OH, OH. Okay, so this is your diarabinose. I am going to have you do this reaction and name them. Okay, so for here, these 5 carbons stay fixed. Okay, so the bottom ones definitely stay fixed. Okay, but we're going to add another carbon at the top, which becomes our new carboxylic, our new aldehyde. Okay, but this carbon here, half the times it goes this way. The other half of the time, it goes this way, but otherwise it remains unchanged. So we're just extending this out 1 carbon longer. Okay. So if you look at this one is the glucose, so this is D-glucose. And I think this is mannose. Mannose, right? D-mannose. Oops. Mannose. Okay. So if instead I gave you the Vold degradation, okay, the degradation you're making it one carbon shorter, okay, and so you start with D-galactose, which is here. Okay, so you find that out, right? So like this. So this is your D-galactose. Here you're only going to make 1 product, because what we're going to end up doing is we're going to end up lopping off that carbon there and making this one the new C double bond O. Right. So now this one here, everything else remains the same. Right. Right. So this becomes this. Right. So you look on your chart. So right, left, left, right, right. So left, left, right, right. So this ends up being D-lixose. Okay. Okay, for this. Okay, so for these, for the linkages, first thing you're going to want to do is get the numbering down. Okay, so you have a 6-membered ring. Okay, so this carbon out here that's sticking out is going to be 6. Okay, so by that, so it becomes 6, 5, 4, 3, 2, 1. So for here, right, this is the 6, and so you just work backwards. That's the easiest way to do this. A student told me that. So 5, 4, 3, 2, 1. Okay, so for this one here, here's that. So 6, 5, 4, 3, 2, 1. Okay, so and this one here, right? 6, 5, 4, 3, 2, 1. Okay, so common mistakes. One is to forget that there's a carbon out here. The other thing is forgetting the carbon here, because if you get to this point, so if you're going backwards and you get to this point and you're not at 1, you're not going to count this. It's an oxygen. You're just counting carbons. So if you get to this point and you're at 2, something's happened. Okay, so with that, so you've missed 1. So go back and you can put in your dots, right? 1, 2, 3, 4, 5, 6, right? So with that, so okay, so for this linkage here, right, we're interested in, we just have to look at these 2 sugars. This is the left-hand sugar, okay? This CO bond here, coming away from the left-hand sugar, it's pointed down, so that's alpha, Okay, and then you're going from 1 to 6. Okay. Now we reset. Now we're looking at this linkage, so now we're just interested in these two sugars here, right? And so for this one here, it's going up from the left-hand sugar, so it's beta, and it's going from 1 to, it's going up to here, so it's beta 1,4. And then for this one here, now this is the left-hand sugar, okay? Because all we care about are these two. This is the left-hand sugar, and so for this one here, right, it's pointed down. Okay, so it's going to be alpha carbon 2 to carbon 6. There we go. Good luck.